Hi, welcome back, folks. This is problem 3 on the practice exam. So this problem doesn't involve much math. It asks you to imagine forces acting on someone standing in the middle of a subway car as that subway car does various things. So here I'm asking you to draw the arrows in the force diagram proportional to their sizes. So let's just do them one at a time. So part A, subway car is just going forward at a constant velocity. You know, if constant velocity means there's no acceleration. If there's no acceleration, all the forces sum to 0. So my person in the subway car, this is a view from the rear. So we're looking at the person horizontally. And the two forces, the normal force and gravity, must have equal magnitude because their acceleration is 0. For number 2, so we did this one. For number 2, we will also do a rear view. Here, if I'm accelerating downward, well, I don't need any forces to the side, but I know my net force has got to be down. So that means that gravity points down, but the normal force pointing upward is not so big. If my acceleration downward is 3 meters per second squared, then this is only going to be 2/3 as long as that one. I notice the colors have started to go a little bit wacky. So I'm going to, well, I'll change it after this video. So pardon the colors getting a little bit red tinted. The sun's setting outside. I can fix that. Part C, imagine us turning left. Well, this is again going to be a rear view. So if I'm turning left, so now my acceleration is to the left rather than to the down. So I have my normal force and gravity of the same length. But if I'm accelerating to the left, there must be some other force pointing to the left. And in this case, since I'm standing on the floor, that force is going to be static friction. Since coefficients of friction are less than 1, and this train is turning gently, then this arrow is going to be less than the normal force. Part D says, what if I am accelerating forward? Well, if I'm accelerating forward, I need a way to draw an arrow pointing forward. So now I have to draw the force diagram looking at the person from the side. So in all of these, this is up, down, left, right. But now I'm looking at my person from the side. So now my coordinate axis looks like this: up, down, front, back. I again have my familiar normal force and gravity. So here, those are the same length. But now, friction, rather than pointing me to the left, now points me to the forward. So those are parts A through D. Part E says, and I'll just read it, anyone who's ridden a subway car feels themselves thrown backwards when it accelerates forward. What force pushes them backwards? If there is no such force, then explain why they feel themselves thrown backwards when the car accelerates. So this is getting at the ideas of being in an accelerating box that we've talked about since we put Kiki in an elevator and had her jump and try to hit the buttons. If the subway car is accelerating forward, then I will not accelerate forward too unless some force pushes me forward. Absent that frictional force, the subway car will accelerate without me, and the subway car moves forward, I will not, until the back of the subway car finally hits me in the butt. From my perspective, it looks like, well, the room in front of me went forward and I moved backwards relative to the subway car, unless some force pushes me forwards. So from my perspective, it feels like, oh, there's now a static friction force pushing me forwards. From the floor, right? The pole I'm holding onto or the floor that I'm standing on now pushes me forward, so my feet go forwards and the rest of me goes backwards. It has to do with, again, the relative acceleration between the box that you are in and what the forces around you make you do. Again, you're in the subway car is accelerating, but you don't without some force pushing on you. Another way to think of this is, and this is more technical than you would need to go into, but if I am in a box that's accelerating, I could write the sum of the forces that are real equals my mass times the total acceleration. But if I'm in an accelerating box, let me break the total acceleration up into two pieces, the acceleration of the box plus my acceleration relative to the box. This is an elevator, a car, a subway car, anything you like. And now, if I wish to pretend I am not accelerating, even though I am, if I want to pretend that I'm not in an accelerating box, I can just subtract that from both sides. So I have the sum of all of the forces that really exist minus the mass times the acceleration of the box equals m times a relative to the box. So I get an equation like this again. If I am in an accelerating world, but I wish to pretend that I'm not, I take this term and I put it over to the left where all the forces go. This is not a force. Acceleration is not a force. But I can make it act like one mathematically if I just pretend that I'm not in an accelerating train car. So that sort of pretending creates a fictitious force, a fake force, opposite to the acceleration of the box that you're in. That is another way to explain this with more math. You don't need to do this, but that's kind of a more technical way to do it. So that's problem 3. Are there any questions about that before I move on to problem 4? I'll ask from the Twitch and Zoom people watching here. All right. So we're going to stop recording now.